Cool guys, so question 8 of the grade 12 June 2025 math paper 2 paper. We have 8.1 here. In the diagram below, A, B, and C are points on the circle with center O, okay? Prove the theorem which states that AOC equals 2 times angle B. So this is a 5-mark question and we have to prove this theorem. This is quite a common one. They do enjoy asking it and it is grade 11 one, so it's very likely that they will ask it in your June paper. So what we have to do in order to prove this is construct a line from B through O, and we have to write the fact that we construct a line. So we say construct line through O from B. And this creates O1 and O2 over there. We did this construction because we are dealing with two triangles. We're dealing with triangle BAO and triangle BCO over here. And we're dealing with them separately. So the first point we have to do is we have to say AO equals OB. This is because radii. Because AO and BO are the same length, it therefore means that this angle here is the same as that angle there, which means OAB equals OBA. This angle equals that angle, and we're going to call them x. And our reason is because angles op equal sides. So we know that this guy is x, this guy is x2. And then last move for this triangle, BAO, is that O1 equals 2x because of exterior angles of a triangle. So this guy plus that guy equals this guy over here. We can do interior angles of a triangle and then do angles on a straight line, but we can jump straight to it with the exterior angle of a triangle, that this x plus that x equals O1. So therefore O1 equals 2x because of exterior angle of triangle. So at this stage, OBC is exactly the same. We just have to basically repeat this whole formatting here, just in triangle OBC. So I'm going to do it quickly, saying OB equals OC. Radii is our reason. Now that we have that, therefore, this angle B here equals angle C here equals Y. We can't assume that it is also X here because we don't know how this line intersects this angle B, whether it bisects it or not. So we're going to call this guy Y. So therefore, OBC equals OCB equals Y. So we have a Y there and a Y there. And once again, that is the same reason as here. Angles op equals sides. Great. And then once again, O2 equals 2Y over there because exterior angles of a triangle. Great. We're almost done. We're in the finishing stage where we're just setting up the equation in terms of X and Y, proving that AOC equals 2B because ABO plus CBO equals X plus Y over here. But then we're going to do the same thing here, that AOC equals 2x plus 2y. So we have proven both of these already, and therefore AOC, if we were to factorize the 2 out of here, we would say 2x plus y over there, and therefore this guy, AOC, is 2 times the size of this whole angle here. And we can just finish our statement by writing this final answer, that AOC equals 2B. And we have just proven that angle at center equals 2 times angle at circumference, earning ourselves 5 marks. Great. So 8.2 in the diagram below, BC is parallel to FD over there, okay? And C3, this guy over here, equals X, and then AFB and EFC are straight lines. So 8.2.1, determine giving reasons for other angles that are equal to X. So 4 other angles that are equal to X. Off the bat, we have tangents from the same point. So therefore, CD equals AD. Because of tans from same point, therefore A3 also equals C3 because angles op equal sides. So we have one angle here that makes this statement true. We can then go ahead and prove angle B equals A3 over here because tan chord theorem. So we have a triangle ABC over there, and therefore this angle A3 equals angle B over here. So we can write A3 equals angle B because of tan chord theorem. Okay, so now that we have that, we have B as well. And then from B over here, if we were to look at BCEA, we have a bow tie going on there, which means that our angle E relative to our angle B here is exactly the same because of angles from same segment. So B equals E, angles in same segment. And then we're almost done. The only other thing missing and that we haven't used is the fact that these lines are parallel, which means that B over here equals angle F2 over here because we have an F over here. These parallel lines, therefore B equals F over there. So we have angle B equals angle F2 because we have corresponding angles. And then we just have to write the parallel lines. We have FD is parallel to BC. So those are the 4 other angles that are equal to X. We have A3, we have B, we have E, and then we have F2. Okay, and then at this stage, it says prove that AFCD is a cyclic quadrilateral. Okay, so they're saying AFCD over here. So if we were to connect them, it would be something like this, for example. So whenever we're proving a cyclic quadrilateral, there are a couple ways to prove it. We can either look for a tan chord theorem, so some sort of exterior angle going into a triangle and those two equaling to prove the converse tan chord theorem. We can also look for converse of opposite angles of a cyclic quad supplementary. If we can prove 180, then we can prove that, but we don't have any angles, so we won't be proving that. Another very common one they like to ask is the converse of the angles in same segment. So if we are in AFCD over here and we are trying to prove that a circle could be drawn perfectly around those points as if they were all touching the points on the circle, we can then go ahead and prove the converse of angles in same seg. So we're looking for a bow tie, and the bow tie that we're looking for is over here, because over here, based off of this previous question that we just calculated, getting 4 other angles that are equal to X, we know that F2 is equal to X and this original C3 is also equal to X, and these two guys are both angles in the same segment. So we can just go ahead. It is only a 2-mark question, which means there wasn't a lot of work for us to do. This was the follow-on question to help us prove this question. We can just go ahead and say F2 equals C3 equals X. This was proven already, and because of that, therefore AFCD is a cyclic quad. And our reason for this is converse angles in same seg. And we have just proven that AFCD is a cyclic quadrilateral for 2 marks. And now we're on 8.3. This is the last question of this section. So 8.3, in the diagram below, AC is the diameter of the circle with center O. So we have a center, very important. AC is produced to P, so it's just an extension of a straight line. B1 plus B2 equals 127 degrees, okay? And P equals 16 degrees over here. So it's saying show giving reasons that BP is a tangent to the circle at B. So this is a 5-mark question. It looks like a tangent, but we can't assume it is a tangent here. So in order to prove a tangent, we have to look for some sort of tan chord theorem, considering we have a triangle inside our circle. So the first move we want to do here is note that our AC is our diameter. If ever we have a diameter, we can cover up half of the circle, which means we have angle in a semicircle. It means we have a right angled triangle over there, which means this is all shaded. We have an angle in a semicircle, and that means this B1 over here is 90 degrees. So we're going to say B1 equals 90 degrees, angle in semicircle. So we have 90 degrees here. A reminder that we're trying to prove the converse of tan chord theorem, meaning that we're trying to prove that B2 over here equals angle A over here. So if we know that B1 equals 90 degrees, it means that B2 is the remaining portion, which means we can take 127, subtract 90 from it, and we'll have B2. So this is just working out. There's no reason here apart from the fact that 127 was given to us. So therefore 127 minus 90 equals B2, and B2 therefore equals 37 degrees. Okay, so that means if B2 equals 37, we're trying to prove that A over here equals 37 as well. And what we can do, considering that we knew that this whole thing is 127, we can look inside triangle ABP over here, and we can do interior angles of a triangle. Once we've done interior angles of a triangle, we'll see that this angle here, A, also equals 37 degrees, and then because those two angles are equal, B2 equals A, then therefore we can prove that it is a tangent using the converse of tan chord theorem. So therefore A plus P plus B equals 180 degrees. This is because interior angles of a triangle. Cool. And then A is what we're trying to figure out. But then P equals 16. That was given to us. B as a whole equals 127. That was given to us. And this equals 180. Then we can go ahead, add up the 16 and 127, take them over and subtract them. So 180 minus 127 and minus 16 equals 37 degrees. And that is great for us considering that B2 equals 37 degrees and A also equals that now. So therefore B2 equals A equals 37 degrees, and therefore BP is tangent because converse tan chord theorem. Okay, and that is our final answer, and that just earned us 5 marks and 17 marks for this whole section. Great job, guys. Let me know if there are any questions in the comments below, and then I will see you in the next video.